So believe it or not, we are already at the last video of this chapter. As I've mentioned, chapter 7 is the quickest one in the book. But each lesson is packed full of all this new stuff that you guys have to keep straight. So definitely make sure you're looking back, not letting the tests go by without studying too much. You've got to prepare if you want to do well with this. There's a lot of content in these 4 lessons. What we're doing in this lesson is we are continuing our discussion of X bar's graph. At last video 7.3a, what we learned was that if the population is normal, X bar is approximately normal. But we didn't talk about what happens if the population isn't normal. And that's where things are going to start. So I've got a link to the same applet we learned last time, or we looked at last time right here. But last time we only worried about if my population started out normal. What I want to do is just make a really crazy looking population right here with all sorts of stuff going on. So that's my population that I'm interested in analyzing. Okay, so I'm starting out with that population. And I'm going to start my sample real small. I'm going to go a sample of size 2. So what it is going to do here is it is going to pick 2 dots out of this picture. It's going to average those 2 dots, and it's going to give me a dot. This blue guy here is my X bar sampling distribution. And I'm going to do that a couple times. Again, you guys saw this last video, so you should have an idea of what it's doing. It's averaging those and giving me a dot right there. And if I keep on doing this right here, a bunch of times. So I've gone, I don't know, 200,000 times. Wow, I did a lot of reps right there. That doesn't look normal to me. So we've got a situation where we've got some dips in our data set, and it does not look approximately normal. Okay? That was size 2. So what I'm going to do now, let me see. I'm going to clear that out, and I'm going to raise my sample to size 10. So I'm going to do the same sort of thing, show you 1. I'm not going to do it as many times. It's going to average those 10 dots. It gives me a dot for my X bar, and I'm going to do that 10,000 and so on. So actually, that guy does look somewhat normal. I wish I could move the scale around on this so we can see better, but perhaps that is approximately normal. What I'm going to do now is make a different picture and try a different looking population. So this time, I want like a super U-shaped population right here. If I take samples of size 2, so 2 dots, average, etc., let's see what happens as my graph goes. I get this really interesting looking picture right here. So that totally doesn't look like my picture. Okay, it's not an approximately normal setup. But if I raise the sample size right here to 10, and I do a bunch of them, does look approximately normal. If I raise it to 25, also looks approximately normal. So sometimes the graph looks approximately normal, but it sort of depends on how big our sample is. All right, that's the idea I want to get across right here. So let me go back to my slides and get this set up here. Now that we have an idea of where this is going to head. So what is the shape of the sampling distribution of a sample mean when the sample is not taken from a normally distributed population? Turns out that it actually depends. Does the sample size matter? Yes, it very much does. If the population is normal, we're good. Your sample size could be 2, could be 5, could be 1,000. I don't care. X bar looks approximately normal. If your sample size is not, your population is not normal, then it depends. What can happen is it depends on what your shape looks like and how big your sample is. So I had a good example right here. I did this on that applet. And when I did size 2 versus size 5 versus size 10 versus size 25, you see, first of all, that the variability decreases. We've talked about that all chapter long. Super important observation is that bigger sample size means less variability between samples. In your lowest sample sizes, the graph somewhat resembles the population. Sort of looks like my population over here, And as the sample size progresses, we get more and more normal looking. To give you guys another example, we did that penny problem. And we didn't do as many different sizes in the penny problem, but we had our population. Population was super skewed. Okay, I did newer years over on this end. So we had a pretty skewed picture going on right there. Then what we did is we looked at X bar where the sample was 5. And in that situation, what we found was it still was a little bit skewed. It wasn't as spread out, but it still sort of resembled the population. And then when we got over to sample size 25, and we looked at X bar, what we found was that it wasn't skewed anymore. We actually had an approximately normal looking picture, and the mean of this picture ended up being the mean of our actual data set right there. So as your sample size gets bigger, your graph gets more and more close to a normal distribution. And honestly, if you look at these, when I was doing my examples on the applet, even 10 looked pretty solid right here. But where is the cutoff that we consider like good enough where we're pretty certain it's approximately normal? We actually use the cutoff of 30. And this result is called the central limit theorem here. So let me get everything up on this slide and we'll talk about this. Central limit theorem is a tremendously important statistics and probability concept, and there's actually a lot more to it that I'm not talking to you guys about in AP Stats. So if you see this in college, you'll do more with it there. What you need to know in AP Stats about the central limit theorem is that if your sample size is big enough, if the population distribution is not normal, the central limit theorem tells us that X bar will look approximately normal if n is greater than or equal to 30. Okay, so 30 is the cutoff for your sample size that we use. And then if it's at least 30, X bar's graph, approximately normal. That's actually it really is a big deal, because what it's saying is it doesn't matter how like crazy looking your population is. My population could look like this. It doesn't matter how crazy that population is. If you take at least 30 data points out of this data set, your X bar graph will still look normal. This is a huge deal. Really, really important. First semester, chapter 2, when we learned about normal CDF, it's like, okay, yeah, this is really good. This is useful. But what about stuff in real life that isn't normal? Because not everything is. It doesn't matter how crazy your original data set is, the average of those data points will look approximately normal as long as your sample size is at least 30, which isn't that hard to do. So if I'm looking at all of St. Louis for some, I don't know, ACT score, number of texts that you send, number of times you've gone through red lights, whatever I'm looking at. If I can pull at least 30 people, the graph of those averages will look normal if I have enough data, which is a really, really helpful thing. Really, really important. So if the population is normal, it doesn't matter. You can be sample size 2, you're good to go. But if the population is not normal, that's when you use this new results. So let's look at a big example problem here. And then that's pretty much, as far as I recall, where that's basically all we need to do is go through a big example here. Same sort of setup as last time. So the number of texts sent by a typical day by a randomly selected high school student, we're saying that it is right skewed. So most of you probably don't send too many texts. I could make this more relevant and talk about like Instagram posts or TikToks or whatever it is you kids learn about use nowadays, whatever social media you like. But we're talking about how many posts or texts or whatever you guys send. We're saying the mean is supposed to be 15 and the standard deviation is 35. Those are the population values. We are looking at kids at our school, and we're looking at a sample of 50 kids, and we want to figure out what the probability is that if I pick 50 kids, between them, they will have sent a total of at least 1,000 texts or more than 1,000 texts. Okay? So that's just a total. That's not an average. So you may be looking at this like, okay, what happens now? But if you know the total and you know how many of them there were, it wouldn't be that hard to find the average. All you need to do is actually divide it. And if you divide these two things, that's going to make 20. So this problem is basically saying, what's the probability that if you pick 50 kids, the average is above 20? That's what it means. Okay? So the first thing you have to do, if they give you a sum, divide it by how many people there are, and you got yourself an average. So they are really asking us in this problem, hey, what's the probability that the average for your 50 kids is greater than 20? Okay, so we've established, all right, we're doing a problem with probability and averages, x bars. It's chapter 7 time. First thing we do is we establish our variable. Our variable in this problem, it's an average problem. We're going to do mu, just like last lesson. Mu is going to be the true average number of texts sent by a high school student. And what I want to do is I want to look and decide if x bar's graph, because I'm looking at what I get from my sample, is that graph going to be approximately normal? Well, if my population was normal, like in the peanut problem, done. I'm good to go. But it says in this problem, actually texts are right skewed. So most of you guys don't make too many posts on your Instagram or your TikTok or whatever, but some of you make lots and lots of posts. So it's reasonable to assume the population would be right skewed. Okay, so we've got that going on. But that's not a problem for us. We're still good because even though my population is skewed, x bar will be approximately normal since the sample size is over 30. So since n equals 50, which is greater than 30, the distribution of x bar is approximately normal. X bar's graph is still normal, approximately normal, even though the population is not. So that's the first thing you do. Okay, cool. That means I can draw a normal curve. I can label it for x bar, almost out of space there. But what do I put for my mean and for my standard deviation? Well, don't you worry. We're going to find those out right now. The mean for x bar's graph is just the mean for the population, which they say is 15. And standard deviation, I got to check 10% first. 50 is less than 10% of high school students. That's great. That means it's standard deviation time. The standard deviation for x bar's graph is not just that 35. You got to take the 35 and you have to divide it by the square root of n. So I'm going to take 35 divided by the square root of 50, because that is my sample size. And if I divide that out, 35 divided by square root of 50, it's like 4.95. So I'm going to label up my picture right here. And actually, this would be a great chance to pause the video and try to finish this off yourself. I've given you what you need right here to get it done. So if you want to pause me and try it, that is cool. I'm going to go ahead and label my picture. And then I'm going to come back with my answer because I am out of space right here. Okay, I'm back with the solution here. Written up here in orange, I have my normal CDF, got about 15% for the probability, and then I wrote out a little statement for what's going on. Let's take a step back and appreciate what we're even doing when we do a problem like this. If we happen to know the real answer, so the actual answer in this problem, the actual average was 15, we can figure out how rare it is to get numbers that are farther away from 15. So here's my 15. And then like a 20 is what I was looking at. You can figure out how rare different samples are. That ends up being really, really useful for us when we learn about statistical significance in more detail later on this semester. So it's a very important skill for you to be able to handle. And you can kind of recognize one of these problems when they start talking about the probability of getting a certain sample. Okay? So that is pretty similar, honestly, to last lesson. The only difference is you say n is greater than or equal to 30 instead of saying the population is normal. Otherwise, that was the same sort of setup as 7.3a. So we've got our little picture right here. I don't need to say a whole lot about this. If you take lots of samples and you calculate their mean each time and you graph x bar, your sampling distribution will look approximately normal with the standard deviation and the mean right there, assuming either the population is normal or your sample size is big enough, at least 30. So this chapter introduces a lot of new symbols that you have to know. See how many of these you can remember. You can just say them out loud to yourself, what they actually stand for. I'll pause, I'll throw up the answers, and that'll be chapter 7. All right, so here are all of those symbols kind of defined for you guys. I won't go through the whole list, but just realize when we're making graphs, those approximately normal pictures that we look like, the things that we know are normal are either p-hat's graph or x-bar's graph. They both end up being approximately normal. That's why we spend so much time on them, because they're nice and we already understand normal stuff, but they get us a lot of different contexts. The two things that can be approximately normal are one of these. You just have to keep straight when they're approximately normal. With p problems, it's that large counts. So n times p, n times 1 minus p, both greater than or equal to 10. And for x bar, it's either the 30 thing or it's the population being normal. Either of those could work out. So if you've got that going on, most of these problems end up being just a normal CDF.